Hi everyone, I'm Fraser Cain. I'm the publisher of Universe Today. I've been a space and astronomy journalist for over 20 years, and this is our question show. Your questions, my answers. Now, wherever you are across my channel, if a question pops into your brain, just write it down and I will gather a bunch of them up and I will answer them here. But we record this show live every Monday at 5 p.m. Pacific time. Oh, we're back to Pacific Standard Time. But so there will be a link to the next event somewhere here on the channel. And if you want to come and join us, you can. Again, you can ask questions in the chat, follow on questions. You can chat with other people. It's a lot of fun. Now, you're going to see some codes up in one of the corners of the screen. And I'm not going to guess which one it'll be because Chad will just do the other one. But those codes are your way to vote. So if you hear a question that you really like, just write down the name of that code in the chat down below. You can add more of a question if you want, but just make sure that code is in there and then we will count them all up and we will give a huge congratulations to the person who got the most votes. And this week, the vote was to Bobo Logic. It was the first question and it was about why bother spending money on science when there's so many issues around to deal with on Earth. And I guess people liked my impassioned answer to that age-old question. And Bobo later told me that they were just being the devil's advocate. So, well played, Bobo Logic. Well played. I hope you can now use this argument when your friends ask you. So, congratulations to Bobo Logic. Let's see what the votes come in for next week. One other quick piece of news, and that is the book club. So I mentioned last week that we've set up a new Goodreads club for the book club. And this is a place for you to suggest books for me to read. And I think that is as complicated as we're going to make the book club for now, is you recommend books that you want me to read. I will read them. And then I will tell you what I thought. And it'll probably maybe one book every 2 weeks. And I will get back to you, or maybe more if I get really enthusiastic about it. So there'll be a link in the show notes to where you can go to this book club group. And you can just start recommending books, vote on the ones that other people have recommended. And I promise I will read one of these books continuously and report on what I liked. And then if we want something more complicated, we'll figure that out. All right, let's get into the questions. Robbie Ostendorp. Hey Fraser, if everything gets cold and the universe runs out of juice due to increasing dark energy presence, could we harvest the dark energy itself for energy and push humanity's shelf life a little bit further? So right now, dark energy is this mysterious force that is accelerating the expansion of the universe, and astronomers don't know what it is, but it seems to be some inherent repulsive force that just comes from space itself. And so as the universe expands, or as the universe gets less dense, you have more and more space that is being created, that is opening up. And for every new cubic meter of space, there's a tiny little bit of dark energy that begins blowing outward repulsively in that cubic meter of space. And so you add light years and light years and you're getting more and more dark energy. And so right now, it's 70-ish% of the universe. If you use E equals MC squared to add up all the energy and all up the mass, it's mostly dark energy. But it's going to be so much more dark energy in the future. Eventually, it'll be 99% dark energy because there's more space, there's more dark energy, there's more space. And so the natural question is, it uses the word energy. Could we harvest it? And the answer is maybe. I mean, we don't know what it is. And so, of course, the classic is, if it's unicorn tears, how do you harvest unicorn tears? I don't know. Someone's going to have to figure out what dark energy is. And then if we can figure out what dark energy is, then maybe we can harvest it. Whatever it is pushing apart space itself. So it is having some kind of impact on the universe. And so that means maybe there would be some way to extract it. So that's the good news. The good news is that dark energy, as long as it's a thing, and if there's a way that we can extract it, it will always be present in the universe, now and forever, assuming it doesn't go away. But if you have a cubic light year of space, there will be a certain amount of dark energy that is pushing outward in that cubic light year of space. If you somehow enclose it, then you can harvest the energy from it. In theory, but like so many conditions apply in like, if we don't know what it is, if we can't do it, then it can't happen. But I'm definitely not going to shut down the possibility we don't know what it is. However, it's not very much. And this I know is going to sound really weird because it is the dominant force in the universe. It is the dominant amount of stuff, energy. And yet, when you look at the amount of dark energy that is being generated in every cubic meter of space, the density is 10 to the negative 27 kilograms per meter cubed. So what that means is that if you had the total amount of dark energy that was being generated in the Earth, it would be about a milligram of mass via E equals mc squared, right? So if you turn a milligram into energy, that's how much you get for the amount of dark energy that is being generated on the size of the Earth. And that's not a lot. So if you wanted to match the total energy output of the Earth, you would need to essentially harvest the dark energy from a region of space that's about 30 light years across. So imagine a sphere that's about 30 light years across. That's how much space you would have to control and be harvesting the dark energy that's pushing against it. So it's not zero, but it's not much. And it requires engineering at a scale we can scarcely imagine. And yet, if there's some futuristic civilization and they've run out of every other form of energy, maybe they'll be able to figure this out. Or maybe they won't. And of course, when I mentioned the heat death of the universe, I had a lot of people going, well, what about this idea for us to overcome the heat death of the universe? Or that idea to overcome the heat death of the universe? And, my blanket answer is that if you can figure out a way to harvest energy from the universe, you haven't reached the heat death of the universe. The definition is when there's no more energy to harvest. No matter how many creative ideas you can come up with, you've used them all up. You've run them all out. There's nothing left. That's the heat death. Ido Deckers. Hey, Fraser, are the stars in the pillars of creation closer or farther from each other than the stars in our region? And is that area inhospitable for now? So on average, stars in the Milky Way are about 5 light years apart. So when you think about it, it's like 4.26 light years to Proxima Centauri. It's about that amount. And, the stars are going to be a little closer near the core of the Milky Way. They're going to be farther apart, closer to the edge, less dense above the disk, less dense below the disk, etc. But if you go into a star cluster like the Eagle Nebula, which is what contains the pillars of creation, or the Orion Nebula, they contain stars at an average distance of about 1 light year apart. So on the one hand, just think how cool that would be. You could be on a planet orbiting a star, and you're looking out into space and you're seeing stars that are packed around you. Like in the Eagle Nebula, there's about 8,000 stars. And you would probably see them all because they're maximum about 30 light years away from you at the most. And so you would see these 8,000 bright stars all around you. Just the night sky would just be ablaze. Is it dangerous? No. I mean, the radiation, if you're close to a star and the star is pumping out tons of radiation, then that's a problem. But once you're far enough away from the stars, you're not going to be getting a lot of radiation. The cosmic radiation that is the most dangerous, that's coming from supermassive black holes. That's coming from supernova. That's coming from pulsars and magnetars that are in your galaxy, in different galaxies, billions of light years away. So the radiation coming from all the stars around you wouldn't impact you. You're always just going to have to worry about cosmic radiation. Dwayne. Hey, Fraser, it appears there's new star formation in the Eagle Nebula. Is it correct that due to random walk, the light we see from those stars was created in the star's core millions of years ago? This idea of the random walk of photons to escape a star is pretty cool. And if you've never heard of it, it's pretty neat to wrap your mind around. So we know that at the core of the sun, hydrogen is getting fused into helium. And this process is releasing gamma radiation as one of the parts of the particles coming together. And this gamma radiation, these photons, are released, but the core of the sun is incredibly dense. And so the photon is released and then it is absorbed by another atom. And then that atom can release the photon and then it's absorbed and then it releases and absorbed. And the direction that the photon is released is random. And what that means is that this photon just goes around in what seems like just a completely random direction. And it may get all the way out to almost the edge of the core of the sun and then into the radiative zone and then go all the way back down into the middle of the core and so on. And it seems, and I've heard different estimates for this, but it can be anywhere between 100,000 and 10 million years for a photon, for when a photon is generated at the core of the sun, for it to finally reach the convective zone. And then once it reaches the convective zone, it then is carried up in these plumes of hot plasma. It reaches the surface of the star within a fairly short period of time, and it can finally get out into space. And so, I mean, is that happening in the Eagle Nebula? Yeah. I mean, this is happening in every star that is not fully convective. So the kinds of stars that are fully convective, these are the red dwarf stars. Like the red dwarf stars, they're all convective zone. They're all like a lava lamp, all of the materials being mixed up. And so any part that is happening in their core is being carried out of the convective zone pretty quickly, and the photons don't have to do this big, long, random walk. But with the sun, you've got the core, you've got the radiative zone, and it's like a firewall that stops between the convective zone and the core from being able to mix up all the material in the sun. And so any star that is bigger than an M dwarf, that is not fully convective, is going to have this random walk. And the bigger the star, the longer the random walk. And I haven't been able to find math that predicts it or estimates it, although I'm sure it's out there and people have done it. But you can imagine if you have a star that is many times more massive than the sun, then that walk is going to be longer, which is weird because we see light coming from the stars. So I'm sure it's a seeming paradox. It is not a paradox, but it's such a cool idea to think that photons. Now, it's not the same photon, right? Like the photon is emitted, it's absorbed, it's emitted again. Is it the same photon? I would say no. It's a new photon. But the total that amount of energy that's attempting to leave the sun has to take time to get from the inside to the outside of the sun. That's kind of why the core is so hot. Anyway, very cool concept, and it would apply to any star that has a core, radiative zone, convective zone. K Maxon 23. NASA said they had a few things to try and get the solar panel on Lucy fixed. Do we know? Did it work? Or is the Lucy mission still running on far too little power? When NASA's Lucy mission launched about a year ago, one of its solar panel arrays failed to latch. And so one half of it latched nicely, and this great big solar panel was able to completely unfurl. But on the other side, it wasn't able to fully sort of think of it like a pizza, and it wasn't able to fully go around the shape of the pizza. And this is a problem. I mean, you're going to have a reduced amount of energy falling on that solar panel, and you're also going to have the potential for it to flap around if the spacecraft does any course corrections, any changes in its trajectory. So this was a problem, and NASA had been working on it for quite a few months. And a couple of months ago, they figured out the best fix that they could do. And they were able to essentially roll out that solar panel to about 99% open. And so based on that, they have enough energy for it to complete its mission. But like the size of those solar panels are really impressive. The problem when you're going out to Jupiter is that you need about 25 times as much solar panels as you do here on Earth to receive the same amount of power. That's a lot. And so if you look at the Lucy mission, the solar panels are gigantic. Same thing with the Juno mission, right? Because Lucy's going to go out to the Trojan belt region of Jupiter. And that's really far away from the sun. And it really shows you, like, Jupiter is like the farthest practical place that you can use solar panels in the solar system. Beyond that, you need to switch to a nuclear RTG, like what's on Curiosity or Perseverance or Cassini or the Voyagers. So at this point, Lucy has enough power. It's not fully latched, but it's good enough, and it'll be able to complete its mission. Armando Miranda. Does matter expand since, in a way, it's still part of space? It just doesn't expand as fast as space does. So when people learn that the universe is expanding, that space is expanding, they wonder, is everything expanding? And then they make a joke about eating too much and that I'm expanding. But are you really? You're not. That's a calorie issue, not a inherent expansion of space itself. So it's back to exercise and diet. And the reason is because, yes, space is expanding at the largest scales. So galaxies are being carried away from each other at the largest scales. But when you have structures that have some method that is holding themselves together, then that will overcome not only just the coasting expansion left over from the Big Bang, but in fact, the additional acceleration that's coming from dark energy. And that sort of balance point is not far when you think about just the size of the universe. It's only a few tens of light years. And so within a few tens of light years, like Andromeda and M33 are definitely within that range, then gravity is what's dominant. And so the gravity between Andromeda and the Milky Way can overcome the expansion of the universe, can overcome dark energy, and they will crash into each other, even though at larger scales, everything else is moving away from us. Within the Milky Way, the mutual gravity of all of the stars, of all the dark matter halo that is holding the whole galaxy together, overcomes this expansive force from dark energy. You can imagine, we talked about it at the beginning of the show, right? Like the amount of dark energy, even though it is what's dominant in the universe, that's because the universe is very big. When you look at any one part of space, that expansive force is very small. And so even though, yes, there is dark energy attempting to push the Milky Way apart, the Milky Way's mutual gravity and the dark matter halo surrounding it is holding it all together. Within the solar system, you've got the gravity of the sun holding all of the planets in place, and dark energy is trying to push them away, but it's so weak that it just can never do it. On the Earth, you've got the mutual gravity of all of the mass on Earth holding itself together. For you have the chemical bonds that are holding your body together. You've got the atomic bonds that are holding your matter together. And so really, dark energy as a force that is expanding the universe really only comes into play at the tens of millions of light years scale. Jay, do you subscribe to the Big Bang Theory, or do you have alternative ideas? I'm just a journalist, so I don't have ideas about the universe. I have ideas about how to run a news organization. I think they're good ideas. But when it comes to the Big Bang, I don't have an opinion. I am not educated enough to have an opinion. All I can do, all that I'm ever doing as a journalist, is to synthesize the work that's being done by other people to attempt to report that. And when I'm synthesizing, I'm looking for consensus. I'm looking for hundreds, if not thousands, of experts who have spent decades working in this field, like just to get your PhD. When you think about it, right? You've got 4 years for your science degree, another 2 years for your master's degree, 3 years plus for your PhD. Like you're in 9 years just to get to the point that you can start doing some new work on the Big Bang. And there are hundreds, if not thousands of people who have put in that work. And my job is to seek their consensus. So when there are alternatives presented to the Big Bang, I like to keep an open mind, but I am not equipped to judge or decide whether or not that is a viable theory or not a viable theory, because I can't do the math. I don't know the literature to that degree. So what I do instead is I watch and see how the scientific community, the hundreds, if not thousands of people who have trained in this, who love to debate and search for any weakness in any theory, especially each other's theories, I watch to see what they do. And if they say that's a really compelling idea, there's a lot of evidence, as I can see minds starting to roll over to this idea, then, I'm taking the temperature, I'm taking the pulse of the community, and I start to shift my reporting based on what seems to be catching the scientific consensus. Like, there was a really great conversation that I saw recently, which is that, like, if you have a theory about the universe, or you want to understand how the universe works, then you have two choices. Choice number one is that you spend that 9 years that I mentioned to study the existing work to get yourself to the point that you understand the existing theory space as well as the other experts in the field. And then you can make your incremental improvement to the field. Or you have to trust the consensus of the people who have just done that work, right? That there are, as I said, there are hundreds, if not thousands of people who have just completed, or within the last few decades, a PhD in this field, have dedicated their lives to studying it. And to dismiss it is ridiculous. Is to say expertise doesn't matter. And expertise does matter, and we depend on it every day. So I have no alternative ideas about the Big Bang. I watch to see as people come up with them, and I watch to see as scientists argue about them back and forth, and I will report on the play-by-play to you. If you like my answers to your questions, as well as the other things that we do at Universe Today, consider joining our Patreon club. You'll get ad-free experience on universetoday.com for life, even if you unsubscribe. You'll get ad-free videos, early access to interviews, as well as other perks that are exclusive to our Patreon community. And thanks to everyone who has already subscribed, and welcome to our recent newcomers: Stefan Lofgren, Barry Mattis, Jeff Sonderman, Scott Holland, Nick, Peter Hansen, Timothy Fukuyama, James W. Valenta, Gary Peets, Joseph Dotz. Join the club at patreon.com/universetoday. John Gomez. If a planet has a massive gravity well and there is intelligent life there, will the intelligent species in that planet be able to escape and go to orbit? I love this question because, like, here on Earth, we live in this gravity well that is just escapable at 1G. And that if Earth gravity was 1.1G, then the modern rocket community that we have today just wouldn't work. Like, we wouldn't be able to launch these heavy space stations and so on. But that's not entirely true. Like, if you were on a planet that had 2G, it would still be theoretically possible to launch a spacecraft. You could build Saturn V, something like a Saturn V, with the same kind of thrust capability. And instead of being able to launch tens of tons to low Earth orbit, you could launch, say, 100 kilograms. So you can imagine if you have some other civilization that lives on a super Earth world, and their gravity is twice Earth gravity, then they have a completely different philosophy about what space exploration means, about orbit, all of that kind of stuff, because they're looking to bootstrap. They're looking to launch whatever is the minimum possible hardware out into space so that they could then gather up resources from asteroid belts, from their moon, etc., and start to build space infrastructure. And so still, I think if you were like a 2G world, you could pull it off. If you were like a 3G world, you might be able to just barely pull it off. Beyond that, it's impossible. And you do kind of feel sad for the civilizations that are trapped in their gravity well for whatever reason, that they can never leave, that all they can do is look out into the universe and see the other civilizations as they zip around and know that they could never overcome the gravity well. And because their gravity well is so fierce, nobody's ever going to want to come and visit them. That said, that's chemical rockets. Like, who knows if we figure out antimatter propulsion or laser sails or metallic hydrogen. And so there could very well be other forms of propulsion that are vastly more energy dense than a chemical propulsion system. And then maybe escape is back on the table. Sean Hall. Fraser, have you ever made a telescope? And if so, how hard was it? I'm thinking of trying it myself. I haven't made a telescope, but it's not that hard if you let someone else do the hardest parts. So, like, the best kind of telescope to build for yourself is a Newtonian, and that is the telescope that Newton first invented. And it is a mirror on one side that then focuses the light to a secondary mirror, and then you have an eyepiece. And so generally you put it inside some kind of tube, and then you put the mirror down at the end, and then you put the secondary mirror up near the front, and then you have your eyepiece. And the real hardcore telescope makers will grind their own mirrors. So you can buy a piece of glass that is the size of the mirror that you want to do, like optical glass. And then you can buy a shape. Like it's like a I don't know. You can then, it's like the shape of the parabola that you're going to be using for your mirror. And then you polish the inside of this glass, and then you use your shape to make sure that you've perfectly got the right curvature on this glass. And then you send off the glass, and you have it silver put onto it so it's reflective. And then you put in the secondary mirror and the eyepiece and so on. It's relatively inexpensive. Like, you can, if you're willing to go through that work, and like, it's brutal. Like, lots of people say, like, I will only ever do that once. And the bigger you go, the more grueling this work is. And so the hack is that you order one. You can go onto Amazon. You can definitely get them from Alibaba out of China. And you're looking for a mirror, like a blank mirror, that you can then put into a telescope. The best way to, like, if you want like an 8-inch telescope, search Alibaba for like a 203 millimeter mirror, and often you'll be able to find a set that contains the mirror and the secondary mirror that it bounces off of. And then everything else is a tube, wood. There's a lot of instructables plans online to do it. And it sounds like work, but it also sounds like fun. I'm kind of planning to do it right now. So there's a friend. I hope he's listening. And my plan is to order a couple of these mirror sets, and we're going to build 2 telescopes together. He's very handy. I'm not so handy, but I kind of know how this is done. So search Alibaba or Amazon for the blank mirror, and they're about $100 for like an 8-inch telescope. And then you have to build the rest, but it's a pretty worthwhile hobby. Let me know how it goes. I'll let you know how mine goes. If I do take on the project, I will document it. I promise. Jason A. Savage, what is the Great Attractor? All right, so either you're trolling me or you're genuinely asking the question. I'm going to assume you're genuinely asking the question. But if you are trolling me, then please let me know in the comments. Well played, Jason. So the Great Attractor is this mysterious gravitational force that seems to be causing all of the galaxies on the far side of the Milky Way to be drifting generally in the direction of this unseen mass. And so because the Milky Way has this dark cloud of gas and dust at the center of the Milky Way, it is opaque to visible light telescopes. Astronomers used to call this, or maybe they still do, the zone of avoidance. In other words, if you're going to try to do any kind of galactic or astronomy work in that region, don't bother because there's just dust. But when they looked at the movements of all of these galaxies across the universe, they could see that a lot of them in our local neighborhood were drifting towards something that's on the other side of the Milky Way. So what is it? Well, it's like a galaxy cluster. And over time, thanks to infrared observatories, which allow you to see through the gas and dust, astronomers have been able to decrease the size of the zone of avoidance and be able to actually start to see all the different galaxies and galaxy clusters that are on the far side of the Milky Way. The reason I'm taking this question on now, even though I've answered a bunch of times, is that actually there was a paper that came out just this week that someone has seen sort of the latest component of the Great Attractor. So another galaxy cluster that's very close to the center of where all of these galaxies are being gravitationally attracted towards them. So, like, what is the Great Attractor? It is a giant cluster of galaxies. And you've probably heard this term, the Laniakea supercluster. So there is just like the Milky Way is part of the local group of galaxies. The local group is part of a larger cluster of galaxies called the Virgo supercluster. And the Virgo supercluster is part of an even larger structure called the Laniakea supercluster. And the Laniakea supercluster, the gravitational center of it just happens like a total fluke to be on the far side of the Milky Way from us. And so it's mildly obscured from our perspective, but because of infrared telescopes, we can mostly see it and map it out at this point. So I use the Great Attractor like the canary in the coal mine. Like there is a level of science explaining or astronomy explaining, space explaining that happens on the internet that is delayed by years and sometimes even decades. And so when people make these videos, these mysterious videos about the Great Attractor, they're digging up science questions that happened 30 years ago that have been largely explained. It'd be like, like, what are quasars? We don't know. What is the Great Attractor? Who knows? What is the Booty's Void? Who can say? No, we know what all these things are. They've been explained. It's fine now. I'm interested in papers and mysteries that unfolded this year. That's the cutting edge of space and astronomy. So, Great Attractor, just a lot of galaxies on the far side of the Milky Way. They had to be somewhere. They happen to be on the other side of the Milky Way. John Copperthorne. If Sun and Jupiter are orbiting around each other, will it have any effect on Jupiter's L1 point, more or less stable? A Lagrange point question. This is so great. It's been so long. Like last week, maybe? I jest. I love getting the Lagrange point questions. Just keep them coming. We just do whole Lagrange point shows, I think. So Lagrange point, that term point, is a misnomer. They're not a point. They're actually a region. And of course, there are 5 Lagrange regions associated with every 2 masses. And so there are 5 associated with the sun and the earth. There are 5 associated with the earth and the moon. And there are 5 associated with the sun and Jupiter. And 2 of Jupiter's Lagrange points, the L4 and the L5, are exciting. Those are the Trojan regions, which is where the Lucy mission, callback to the Lucy, is going to explore both of those Trojan regions. L1, L2, and L3, the ones that line up between the sun and the body, are gravitationally unstable, which means that if you put something there, it will fall out of it and not be in Lagrange point anymore without some kind of propulsion, like the thrusters that James Webb has on board. But L4 and L5 are gravitationally stable. They are sort of like, that's why you have all of these objects in the Trojan belt. So the question is, if the sun and Jupiter are orbiting around each other, would that have any effect on Jupiter's L1 point? And the answer is absolutely. But there's more than that, right? The whole reason why JWST needs to have some kind of propulsion on board as it hangs out at the L2 point is because it's not a point, it's a region. And you've got, in the case of the Earth and the Sun, the Earth is on an elliptical orbit around the Sun. You've got the gravitational interaction of the Moon. You've got the gravitational interaction of Mars, of Venus, of Jupiter, of Saturn, of Uranus, Neptune. All of these are interacting with the L2 region around the Earth, and they're causing it to be not a point, but a blob. And you will always be, like at any moment, there will be a point that is exactly the L2 point. But then as the moon gets closer and as the Earth goes around the sun, it gets closer to the sun and Jupiter comes into view, then now the position of that point is moving around. And when you think about JWST, it's always chasing that point, trying to get as close as it can to the theoretical perfect Lagrange point. And you're going to have the same thing at Jupiter. And yeah, I mean, Jupiter causes a slight wobble to the sun. It's not much. It's definitely not outside the surface of the sun. But then you've got the gravitational interaction of all of Jupiter's moons. You've got all of those objects in the Trojan belt. You've got the influence of Saturn. I feel like we're going to do its zodiac here. But yeah, so just in general, all Lagrange points are blobs. And that's because the solar system is a complicated place. Magic and coffee. Explain how gas becomes stars like I'm stupid. I'm not going to explain it like you're stupid because you're not stupid. So I'm going to explain it as if you had said, explain how gas becomes stars. So you've got like leftover hydrogen and helium from the Big Bang, this primordial hydrogen and helium. And when this stuff has been cooling down since the formation of the universe, right? It started out very hot and now it's very cold, just a few degrees above absolute zero. And then it's just this giant blob of hydrogen that actually contains the mass of many stars inside of it. And then some event triggers a collapse. So like a supernova going past, or maybe like a star moves through a gas cloud, or a cluster comes close, or two galaxies crash into each other and you get these gravitational imbalances. And that causes this cloud to start to collapse. Essentially, the mutual gravity of all of the atoms of hydrogen are starting to pull together. And they would want to just turn into this big ball, right? Mutual gravity is just going to turn this big ball. But what happens is you say it with me, right? The conservation of angular momentum, as you know, there is some overall rotation of this giant gas cloud. And so as the cloud gets smaller and smaller, it starts to spin up faster and faster. And then that actually starts to tear the cloud apart into blobs. And then those blobs start to spin up and they get torn apart and get torn apart and get torn apart. And eventually you've got a piece that is so small it can't get torn apart. But it is still going to be rotating very quickly. And it flattens out, but at the middle, it gets sort of the mutual gravity is pulling together at the center, and then it gets this big disk around it. And that's the planetary disk, with the future star forming in the middle of this gas cloud. And so with a large amount of just hydrogen, helium with mutual gravity pushing together, turning into this sphere, it causes so much temperature and pressure at the core of the star that you can actually start mashing atoms of hydrogen and turning them into helium. And there's sort of a process to go through that. And that ignites the star. You get fusion reactions going off in the star. This releases a tremendous amount of energy into the neighborhood around the star. At the same time, remember we have this accretion disk, this planetary disk. The planets are on the clock to try and scoop up as much of this material as they can to form as big of a sphere as they can, big of a planet as they can, until the star switches on, the radiation blasts out of the star and clears out the neighborhood of everything. And you're left with the star and all of the planets orbiting around it. And that's how a star is formed. All right, those were all of the questions that everybody submitted this week. Thank you, everyone, for both putting them into the YouTube comments and also joining me for the live show. Remember to vote for the question that you thought was the best, and we'll see you next week. If you want to stay on top of all the important space news, join my weekly email newsletter. I send it out every Friday to more than 55,000 people. I write every word. There are no ads, and it's absolutely free. Subscribe at universetoday.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at universetoday.com/podcast or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Josh Schultz and Andrew M. Gross who support us at the Master of the Universe level. All your support means the universe to us.